This is going to be the lecture over cons section 10.2, and we're going to be talking about calculating monitor units. This is pretty important stuff, so we're going to dedicate pretty much an entire lecture just on this section, just to get you used to the idea of what it means to put together an MU calculation. Now, there are different ways of doing this depending on who you consult, but there's a pretty much a general set method for how to do pretty much either SSD or an SAD calculation. One difference that you will see between this and another lecture that I provided is that in con, what you do not see in the denominator down here is a correction for the isodose line. In some cases, rather than going with a 100% line, which would make all of these just fine, you may want to consider going with, say, a 95% line or a 90% line, in which case you have to add an additional factor in here as part of the denominator's computation. And I don't see that present in any of these. So that is something that we will also need to be able to bear in mind as we go through and make these calculations. So I just want to make you aware of that. One of the other lectures that I had was referenced off of a site in which that was included. And I just want to let you know that these methods here are consistent. This section already has examples worked out, which is really good. But one of the things that it does leave out is assigning an isodose line to these computations, which is missing out of these particular formulas. So I just want to make you aware of that. So the summary here is pretty good. So let's just kind of walk through this. Radiotherapy institutions vary in their treatment techniques and calibration practices. So for example, some rely exclusively on SAD type techniques, while others use both the SSD as well as SAD. Accordingly, machine calibrations are carried out in a water phantom at a reference depth for the standard SSD or at isocenter for an SAD. Although most institutions currently use a reference depth of maximum dose for dosimetric quantities used in MU calculations, some prefer 10 cm depth as a reference depth. Kind of depends on where you go and what the training was. In addition, clinical fields, although basically rectangular or square, are more often than not shaped to protect critical or normal regions of the body. Thus, a calculation system must be generally applicable to the above practices with acceptable accuracy and simplicity for routine use. In other words, you don't want to have to do something that's so complex that it's going to take you a long time to do that. Otherwise, it's going to slow things down. But you also don't want to be wrong in terms of how many MUs that you put through. So you have to strike a balance there. Most of the time, in your clinics nowadays, you're going to have a planning system that's going to take care of all of the MUs for you. You're not going to have to sit down and try to figure out exactly what MUs you need to have in order to be able to make this work. The computer system will already figure that out for you. In addition, most of the programs that you have out there will be able to run a second check on those computations and tell you whether or not you're within 5%, which is the usual standard by which you take a secondary method, a secondary system of calculations using the same physics data, and see if you come up with the same MU computation. That is to make sure that you're not underdosing or overdosing the patient. So the formulas here, you can see here for isocentric fields, SAD technique. This is what we're going to be using. You're going to see the MU is equal to dose. That's the dose on top. And on the bottom, you've got all of these factors that you use to adjust the monitor units to be, maybe above or maybe below the dose, depending on what it is you're what conditions you're attempting to have to compensate for. So let's kind of go through these. D, of course, is in the numerator, and it is the dose to be delivered at whatever point of interest you're aiming at. The first factor down here is going to be your calibration dose per MU at some reference depth under reference conditions. So you have a certain amount of dose that is being generated per monitor unit at a certain set of conditions that will, of course, need to be adjusted by all the other factors that you have here. But you have a set amount that you know the machine is going to produce under set conditions. So what are the adjustments that you have to make beyond that? S sub C at R sub C is going to be your collimator scatter factor for the collimator defined setting, field size RC, and that's what that is. So that's going to be another factor. Then you move on to the scatter factor for the phantom. So the S sub P at R is the phantom scatter factor at the reference depth. For the field size R at the surface, that's going to be applicable to your PDD or your non-isocentric fields. The reference depth here is going to be the phantom scatter factor at D, the reference depth for the field size R sub D at depth D. So for the SAD fields, you have a certain depth D at which you do that. Here, this is being done for the non-isocentric fields. This is being done at the surface. Next, you move on, and it depends on how things are done at your particular clinic. Do they measure a tissue phantom ratio, in which case this would be referencing something that is 10 cm deep? That would be your reference. Or is it going to be TMR, tissue maximum ratio, at which you would be referencing the D max for that particular energy? So depending on which setting you have here, you're either going to go with the tissue phantom ratio, or you're going to go with the tissue maximum ratio. So it just really kind of depends on how your clinic is set up. If you are looking here at the non-isocentric fields, you have the PDD, and you also have P sub N DDD. Let's see if it gives a description here. It doesn't tell us exactly what those are. Okay, it doesn't tell us exactly what those differences are, so I will need to further investigate that. But so this is all of these factors are, we're trying to get at what is the ratio going to be, or the PDD going to be at the depth that you wanted, as opposed to whatever reference depth you're using. The wedge factors, of course, if you have a wedge factor, it's going to be at a certain depth, and it's going to be with a certain field size, and it's going to be with whatever off-axis factor that you have for this particular wedge. Now, if you do not have a wedge, then this factor changes to 1. And the reason it changes to 1 is because anything divided by 1 is itself. And what that means is if you don't have anything affecting it, then we're just going to keep whatever this dose is the same for that specific factor. The same thing goes for the tray factor. If you have a tray being inserted for whatever reason, then you have to compensate for that. What sort of effect is that having on the dose? Well, you have to have a factor for that. Your off-axis ratio at depth D and off-axis distance X. I know that's something we haven't really gone through yet, and that is something that we need to talk about. So that is going to be something coming up that we need to discuss. And then finally here, we've got source to calibration point distance, at which D sub cal is specified, or source to point of interest distance at which D is delivered. This is sort of a correction here for the inverse square law effect that we're going to see. But that is for the isocentric fields. For the non-isocentric fields, you see the source to calibration distance divided by F plus D naught. And the F plus D naught should be defined. I believe the F here should refer to your SSD. I don't know why it's not telling me that off straight off. They failed to define that here, and that's not good. So, but that is your inverse square correction. So depending on whether or not you have isocentric fields or non-isocentric fields, you can see a lot of similarities here between the factors that you're going to need to correct for. So let's go through a few examples here and try to see exactly how these things work. So example one, we've got a 4 megavolt linear accelerator, and it's calibrated to give 1 centigrade per MU in water phantom at a reference depth of maximum dose of 1 cm, 100 cm SSD, and a 10 by 10 field size. Determine the MU values to deliver 200 centigrade to a patient at 100 cm SSD, 10 cm depth, and 15 by 15 field size, given that our collimator scatter factor here is 1.02, the phantom scatter is 1.010, and the percent depth dose for 15 by 15 at a depth of 10, SSD of 100, which, let's see if it gives, yes, all of this right here. You can see this is going to be referring to your SSD. This is your field size, and this is your depth. So that's what it's trying to fill in here with all of these numbers. This is your depth, this is your field size, and this is your SSD. So it turns out to be 65.1. So from equation 10.14, the fact that they are referring to a 100 cm SSD should tell you that this is going to be non-isocentric. This is going to be a PDD setup. So it's going to refer here to 10.14. So MU is going to be equal to 200. And the 200 comes from the fact that we're trying to deliver 200 centigrade. So we're going to take this D and we're going to put 200 in. The first factor here is going to be, it is calibrated to give 1 centigrade per monitor unit in the water phantom at a reference depth of maximum dose of 1 cm. So our decal in this particular case is going to be 1. So we're delivering 1 centigrade per monitor unit. The next factor here is going to be the collimator scatter factor. The collimator scatter factor here for our field size, which we are attempting to use a 15 by 15 field, is 1.020, so that's what we put in. The phantom scatter for our field size is going to be 1.010, so that's the next one that's put in. Next, we go to the PDD, and this whole thing right here is going to be the factor. So that whole thing right there, PDD in this case is 65.1. We take that and divide it by 100, so we come up with 0.651. So that's where that comes from. Wedge factor. Do we have a wedge here that we're going to be using? And the answer is no. Since there is no wedge, we're going to go ahead and we're going to put in 1 for that. Next, we go to the tray factor. No tray factors, or no tray, so we're going to use the factor of 1. OAR, This is not telling us that we have any off-axis factor here, so that is going to be 1. And then finally, this mess, the source to calibration distance divided by f plus t naught. Again, I really wish they would have gone, okay, they did define it in this case. This is equal to the depth of reference of maximum dose for TMR and PDD. Okay, finally, good, they got it. So the source to calibration distance, particularly for a 4 MV field, for a 4 MV field, the SCD, source to calibration distance, is going to be 101. And the reason I know that is for a 4 MV linear accelerator, your depth of maximum dose is going to be 1, and your SSD is going to be set to 100. So in this particular case, this SCD is going to be 100 plus 1. So the SCD here on top is going to be 101. Now, it just so happens at the bottom here, we're looking at whatever our SSD happens to be, not so much for when it's calibrated, but for when it's actually going to be used. So if we were using this SSD at, say, 110, that F would become 110. But in this particular case, F in this case is just going to be 100 because that's where we're using it. Also, T sub 0, since we're using a 4 MV accelerator, is also just going to be 1. So when we add these two together, we're going to get 101 on the bottom. So we got 101 on the top, we got 101 on the bottom. If you have 1 over 1, 101 divided by 101, you end up with a factor of 1. You want to square that, you end up with 1. So all of this mess ends up being 101 over 101, and it ends up being 1, and 1 squared is going to be 1. So that's where this last 1 comes from. So finally, you've got 200 divided by this times this times this, and all of these other ones could just as well disappear. When you do that, that's when you come up with 298. So the number of monitor units that you're going to have for this is going to end up being 298. So that's an example of the MU computation. Next, we come up to example 2. We're going to determine the MUs for the treatment conditions given in example 1 above, except that the treatment SSD is now 120. The given collimator scatter at 12.5 times 12.5 is 1.010. And the percent depth dose for the new SSD is 66.7. So the field size projected at SAD is, which is going to be 100 cm. What you see here is that when you change, except the tree, okay. So that when you change the field size projected at SAD, when you change from 100 here to 120, you end up I see. When essentially you're setting the, and this is a little confusing, I think. You're setting a 15 by 15, but you're setting that at 120. When you set that 15 by 15 at 120, you have to go through and you have to figure out where the setting or what that length actually is at 100. The way you do that is you take the projected field size of 15 and you say, okay, I'm going to take the field size at 15 and take the ratio of the calibration length to the length at where it's being treated. So let me kind of hook up the tablet here to kind of show you a little bit better. You may already conceptualize this pretty well, but in case you don't, I can draw a picture here and kind of give you an idea as to what's going on. Let's see if I can get this again. There we go. There we go. Okay. So let me scroll up a little bit. Do the annotation. So we've got, let's see, field size coming out, and it strikes the phantom here. And when it strikes the phantom, we've got a field that is a length of 15 cm. Okay. Tell you what, let's write like a human being, and let's try this again. And this length here is at 120. However, in order for us to be able to get the accurate calibration factor for phantom scatter, what we need to do is, I don't know why I did that. There we go. We need to figure out what's going on here at an SSD of 100. Because while the field is sitting at 15 cm, our collimator scatter factors here are going to be with the length of the field at 100. Now, as it turns out, we take this and we say, okay, I want to know what this length is from here to here. I know this length at 120 is 15. I need to know what that length is at 100. And the way you do that is you take the calibration SSD and you divide it by the treatment SSD in this case. So when you do that, you end up with the field size projected at SAD, you end up with 12.5. So that's why they give you this information, because the collimator scatter factor at 12.5 by 12.5 is this. The phantom scatter factor, which is actually, again, the dealing with the field size at the surface, or in this particular case, since we are dealing, well, technically we're dealing with this equation right here. So again, we're having to go through and we're having to deal with the collimator scatter factor here at collimator defined setting here, but our phantom scatter is going to be the R, the field size R at the surface. So that's where this is coming from. So sorry for the long-winded explanation there, but so the field size here again on the patient is going to be 15 by 15. So that's why they give you the phantom scatter at 15 by 15, but the collimator scatter is at 12.5 by 12.5. So we have these two factors here. Also, the SSD factor, or inverse square factor here, we've got the the source to calibration distance, which again is 100 plus 1, 100 for where it's calibrated at, the 1 for the maximum for a 4MV. And we're actually going to be treating now at 120. So that's why it's 100 plus 1 on top and 120 plus 1 on the bottom. You take that ratio and you square it, and this is the stuff you come up with. So in order to compute the MUs, you still have the calibration factor here of 1 centigrade per monitor unit at whatever conditions. Then you have the collimator scatter factor, then you have phantom scatter factor, then you got the PDD, which they told us here. Now, fun fact, PDD here is higher at 120 than what it was here at 100. And that's because as you increase the SSD, the PDDs increase. So hopefully you kind of noticed that. Our wedge factor and tray factors, those are both the same. There is no off-axis factor. However, since we are adjusting for moving from 100 to 120, then our inverse square factor here is also being lowered from 1. Now, the other thing here that we're not putting into this again is the isodose line. We're still assuming here that we're going to go with 100, so that has not changed. So because of that, then we get to go through and do the multiplication of the stuff at the bottom and multiply all of that out, and it already goes through and just says 200 divided by all of those things multiplied together ends up being 422. So that's where a lot of these numbers are coming from. I just wanted to go through that explanation. Let's go through a couple more here. Example 3. You've got a tumor dose of 200 that is to be delivered to the ISO center, which is located at a depth of 8 cm given a 4 MV X-ray beam. Field size at the center is, at the ISO center, is going to be a 6x6. So your collimator scatter at 6x6. And again, remember, since this is an SAD setup, your SAD setup here is going to be a collimator scatter factor for the collimator defined field size of this. It is going to be something that is automatically computed. And in these cases, it's pretty much going to be given to you. Your phantom scatter at this particular point for SAD, usually this is going to end up matching this. The 6x6 for the phantom and the 6x6 here for the collimator. So you're given both collimator as well as the phantom scatter factors here. The machine is calibrated in SCD of 100. And the TMR, if you're going 8 cm deep at 6x6, is going to be this. So using equation 10.13, which if we go back to, it's going to be this one. So we know this factor, we know this factor, we know this factor. We've been given this, no wedge, no tray, no off axis. This is going to end up being the source to point of interest distance at which D is delivered. And then we've got the source to calibration distance, which is going to be, since it is calibrated at 100. Okay. You'll notice the factor here is going to be 1. And since that SCD is 1, the SPD in this particular case, source to point of interest distance at which D is delivered, as that turns out, that's also going to be 100 as well. So 100 divided by 100, and then you square that, is going to be the 1. So now we know where all of these factors come from. This is our calibration factor, S sub C, S sub P. This is TMR, wedge. This is the tray factor, this is the off-axis factor, and again, this is the inverse square factor, which we said was 100 over 100 squared, which is just going to be 1. Multiplying all of that together, we come up with 265. Now, for example 4, we're going to calibrate MUs for the case as an example 3. If the unit is calibrated non-isocentrically, just to mess with you a little bit, i.e. at SCD is going to be 101. Again, that would be an SSD of 100 plus 1 for the D max, and that's where the SCD comes in at 101. Now, since that is the case, and your SPD is still going to remain at 100, all of these factors except for this one are going to remain the same. This one is going to be 101 divided by 100. And when you square that, you come up with 1.02. So that's where that's coming from. You're taking this, dividing it by 100, and then you're squaring the result. That's where that's coming from. And that's where they end up with the 260. So this is going to be 4 examples of using these formulas up here. I will come up with more and I will put them in for you to work as a homework assignment. Now, after this, we're going to be looking here at some examples here for cobalt 60 calculations. So we're just going to do one. If you will look through here, for cobalt therapy, we're going to use equation 10.14. 10.14 is going to refer to a non-isocentric field, so we're looking at a PDD setup. So The above calculations, in other words, examples 1 through 4 that we've worked, are sufficiently general that it can be applied to any radiation generator, including cobalt-60. In the latter case, the machine can be calibrated either in air or in a phantom, provided the following information is available. If the percent depth dose data for cobalt-60 are used, then the SOP and the TMR can be obtained by using equations 10.1 and 10.5, so on and so forth. So let's just kind of go through an example here and just kind of see what we got. So we've got a tumor dose of 200 at centigrade, and that's to be delivered at an 8 cm depth using a 15 by 15 field size, 100 cm SSD, and penumbra trimmers up. The unit is calibrated to give 130 centigrade per minute in phantom at a 0.5 depth for a 10 by 10 cm field with trimmers up, and SSD is equal to 80. Determine the time of irradiation given the collimator scatter of 12 by 12, the phantom scatter of 15 by 15, and the PDD of 8 cm depth, 15 by 15 at 100 SSD is 68.7. So we're going to go through the same exercise here of a field size projected at SAD, which is 80 cm, is going to be 15, which is going to be the 15 by 15 field size, which again, we're going to scale to get what it would be at calibration. These things, cobalt is going to be calibrated at 80 as opposed to 100. So 15 multiplied by 80 divided by 100 is going to end up being a 12 by 12. And that's why they are giving you these values. So plugging all of this information in, we get 200. And then they are gracious enough here to rewrite the formula here, except time is going to take the place of MUs in equation 10.14. The dose rate calibration was 130 centigrade per minute. S sub C at a reference RC was given to us here as 1.012. The phantom scatter here was given to us as 15 by 15. That's 1.014 put here. Next is going to be the PDD at all of our reference information here, 68.7. So we take that, divide it by 100, and we come up with that. We have no wedge and no tray factor. So both of those are 1. We have no off-axis factor here, as far as I can tell. So I don't know why we don't have another 1 down here. We should, but maybe they reference that here. No, they do not. Okay, so finally here we have SCD, which in this particular case is 80.5 because you're looking at the calibration distance, which is going to be 80. And for a cobalt, your maximum is going to be 0.5. So you add those two together, and that's where that comes from. And then here you're going to have 100 plus 0.5. So when you put that information in here, you got 80.5 over 100.5. That squared ends up being 0.642. So when you take 200 and you divide it by the product of all of those, you come up with 3.4 minutes. So something else that we will need to work on in this particular section, and I haven't really gotten into it that much because I'm struggling trying to figure out exactly how best to approach this, is going to be irregular fields and the scatter that goes along with this. So that will be the next part of the lecture here when I discuss chapter 10, and I may incorporate some other resources here to do that.